Hello everyone, this is Jesse Smith, and in this video we're going to cover a primer on Gauss-Jordan elimination. I hope you will find this a helpful review. Hello everyone, and let's begin with a quick review of the process of Gauss-Jordan elimination. Remember that the goal of Gauss-Jordan elimination is to use the elementary row operations to get the matrix to a simplified form called the reduced or echelon form. In this form, we will quickly be able to find the solutions to the corresponding linear system. Gauss-Jordan elimination consists of two phases. The first phase is called the forward phase. In the forward phase, we begin by finding the leftmost column that is not all zeros and make the very first entry in that column a 1. After that, we make all entries below the leading 1 a 0 by adding appropriate multiples of that row to the rows below. Once we have done that, we ignore that row in the matrix and we restart the forwards phase on the matrix that results. And we continue this till we've walked through the entire matrix. Once we walk through the entire matrix, we begin the backwards phase. So we start at the end of the matrix, at the very last pivot, and we make everything above that pivot a 0 by adding appropriate multiples of that pivot row to the rows above. We then move backwards to the previous pivots, and to do this process until we get back to the beginning of the matrix or our very first pivot. At what point after we make all of the entries above all the pivots 0, we have the reduced row echelon form. Let's work an example together. Our job in this problem is to find the numbers capital A, capital B, and capital C, so that the fraction 81 divided by x times the quantity x squared plus 9 equals a divided by x plus bx plus c all divided by x squared plus 9. This is an application of partial fraction decomposition. To figure out the linear equations and get a linear system, we're first going to multiply both sides by x times x squared plus 9, the denominator of the left-hand side. Doing this, we get the following. 81 is equal to the right-hand side multiplied by that denominator, but we can take that denominator and distribute it through the sum. When we do that, we'll get a over x times this entire quantity, but notice the x in the denominator will cancel with that x to just give us a times x squared plus 9. Likewise, when we distribute it through the second term, the x squared plus 9s will cancel, and all that will survive is the x and the numerator of the fraction. So we get the following. 81 is equal to ax squared plus 9a plus bx squared plus cx, and we get this by distributing. Finally, if we combine like terms, we get 81 is equal to the quantity a plus b x squared plus c times x plus 9a. We can imagine this as a quadratic equation of the form 0x squared plus 0x plus 81. And on this side, we have a formula where this is the number in front of the x squared, this is the number in front of the x, and this is the number without x's at all. We're simply going to set coefficients equal to get three equations. There's no x squared on this side, or there's a 0 in front of the x squared on the left-hand side, so this sum, a plus b, must equal 0. Likewise, the c will have to equal 0, and 9 times a better equal 81. So we get these three equations. I can represent these three linear equations in an augmented matrix of the following form. 1, 1, 0, 0, 0, 0, 1, 0, 9, 0, 0, 81. I'm getting this by taking the coefficients from in front of the variables. In the first equation, I've got a 1 in front of the a, so I put a 1. Then I've got a plus 1 in front of the b, so I put a 1. I have no c, so I put a 0. And that has to equal 0. Likewise, this 0 is going here, this 0 is going here, this 1 here, this 0 here, and then finally the 9 in front of the A, the 0 from the B, the 0 in front of the C, and the 81 to the right of the equal sign. In an augmented matrix, remember, this line represents the coefficients in front of the first variable, the second column represents the coefficients in front of the second variable, the third column represents the coefficients in front of the third variable, and the last column are the answers after the equal sign. To complete example 1, we're going to take the augmented matrix we derived on the previous slide and apply Gauss-Jordan elimination to it. This is the matrix we started with. We begin at the leftmost column that is not all zeros, and we make sure the first slot is a 1. Well, that is done. If the matrix is more complicated, we may have to do row swaps or multiply by 1 over a number in order to make this 1. But in this simple case, it is already a 1. So we move on to making all the entries below it 0. Well, this entry is 0, so nothing needs to be done. So I'm going to get rid of this 9 by adding an appropriate multiple of this row to this row and changing it. So I ask myself, what number do I need to multiply 1 by so that when I add it to 9, I get 0? Well, the answer is -9. So I'm going to multiply every entry in row 1 by -9 and add it to the results in row 3 and replace row 3 by those numbers. If I do that, I'll get -9 plus 9, which is 0, -9 plus 0, which is -9, 0 plus 0, which is 0, 0 plus 81, which is 81. After I've done that, all of the entries below the pivot are 0, so I ignore this row and I focus on what's left in the matrix. I go to the leftmost column, which that's not all zeros, which would be this column, and I make this a non-zero number and eventually make it a 1. In order to do that, I'm going to have to swap these two rows. So I swap row 2 and row 3, which is another one of our elementary row operations, and get this matrix. I now multiply this row by -1/9 in order to make this entry a 1, because I want my leading slots or my pivots to all be 1. So I multiply row 2 by -1/9 and enter the results. -9 times -1/9 is 1. 0 times -1/9 is 0, etc. Now I make sure that all of the entries below that pivot is 0, and it is, so I don't need to do anything for that part of Gauss-Jordan elimination. I now ignore rows 1 and row 2 and look at the matrix that's left. I ensure that the leftmost column of not all zeros is starting with the number 1, and it is, and I make sure that all of the numbers below it are 0, and that's true vacuously because there are no numbers below it. So I'm finished with the forwards phase of Gauss-Jordan elimination. I now begin the backwards phase, and that's where I start with my last pivot and make every number above it 0. Then I move to the previous pivot and make every number above it 0, and I continue that process till I get to my first pivot, and I stop. Here, the last pivot already has zeros above it, so I don't need to do anything. I move to my previous pivot, and I ask, what do I multiply this by so that when I add it to this number, I would get 0? Well, -1 times this plus this will change this row to having a 0 here. So I'm going to do negative row 2 plus row 1. So that would be -0 plus 1, which is 1, -1 plus 1, which is 0, -0 plus 0, which is 0, 9 plus 0, which is 9. That makes all of the entries above the current pivot 0, so I'm done. I move to my previous pivot. This pivot is the first pivot. It has no numbers above it. So I'm actually finished with the backwards phase and finished with Gauss-Jordan elimination. And this is the matrix RREF form, or its reduced row echelon form. From this matrix, I can read off the solution, because if I convert this back to a linear system, this first row means 1 times A plus 0 times B plus 0 times C equals 9. Or put far more simply, A equals 9. Likewise, this row, when I convert it, means B is equal to -9. And this row, when I convert it, means C is equal to 0. So from this, I get my 3 answers for A, B, and C. I've solved the linear system. And if I go back to my original application question, I now have the partial fraction decomposition for my original fraction. Let us work another example of Gauss-Jordan elimination. In this problem, my job is to find the quadratic equation f of x, where f of 2 equals 0, f of 1 equals 3, and f of 3 equals -1. Another way of writing that is to find the quadratic equation that passes through the points 2, 0, 1, 3, and 3, -1. The problem also reminds you that a quadratic equation looks like ax squared plus bx plus c, and our job here is to solve for a, b, and c. Well, since we're given that f of 2 has to be 0, that means if we plug 2 into this equation, we have to get an output of 0. So in other words, a times 2 squared plus b times 2 plus c, which simplifies to 4a plus 2b plus c, must yield 0, and this gives me one of my linear equations. Likewise, f of 1 equals 3 and f of 3 equals negative 1 can give me two more linear equations. So f of 1 equals 3 will tell me that a plus b plus c must equal 3, and f of 3 equals negative 1 will tell me that 9a plus 3b plus c has to equal negative 1. So this gives our linear system to be 4a plus 2b plus c equals 0, a plus b plus c equals 3, 9a plus 3b plus c equals negative 1. I can now put this in an augmented matrix as follows: 4, 2, 1, 0, 1, 1, 1, 3, 9, 3, 1, negative 1. Remember, columns 1, 2, and 3 are representing the variables a, b, and c, respectively, and the last column is the augmented column. It's the output after the equal sign. Row 1 represents equation 1, row 2, equation 2, and row 3, equation 3. This 4 is the coefficient in front of the a, so I put it in the first slot. This 2 is the coefficient in front of the b from the first equation, so I put it in the second slot, first row. Likewise, this c can be thought of as being multiplied by 1, so I put a 1 in the third slot, and that has to equal 0, so 0 goes in the last slot. Similarly, since the coefficients here are 1, 1, 1, that's what I get for row 2, and the output is 3. Likewise, I take these numbers to get the third row of my matrix. So now we have our augmented matrix. At this point, we'll apply Gauss-Jordan elimination in order to find the solution. I'll solve this together with you on the next screen, but I would advise you to pause the video here and try to do it on your own first, and then we'll compare our work together. So please take a moment, pause the video, and try this on your own. Alright, I hope everyone took a few minutes and tried to do the Gauss-Jordan elimination on your own. Now let's look at the solution. I'm going to go ahead and put up the entire Gauss-Jordan elimination process onto the screen. On these first moves, I'm making the first slot a 1 and all the entries below it a 0. On this move, I'm making the next pivot a 1. On this move, I'm making the entry below that pivot a 0 by adding a multiple of row 2 to row 3. In this case, 3 halves times row 2 plus row 3. I then move on to the next portion of the matrix. So after this point, I'm done with row 1, I'm done with row 2, so I focus on this. But that is a 1, and all the entries below it are 0 because there are no entries. So at this point, I'm done with the forwards phase of Gauss-Jordan elimination. I now begin clearing the entries above the pivot, starting at the last pivot. So I think, what do I multiply this by so that when I add it here, I get 0? That would be negative 3 halves. So I'm going to do negative 3 halves times row 3 and add that onto row 2, replacing row 2. So I get negative 3 halves times 0 plus 0, which is 0. Negative 3 halves times 0, which is 0 plus 1, so I get a 1. Negative 3 halves times 1 plus 3 halves gives me 0. Negative 3 halves times 8, which is, what is that going to give us? Negative 12. And then adding that to 6 gives me negative 6. I still need to clear off this 1/4, so the next move there is to do negative 1/4 row 3 plus row 1. So that's my next move. That clears all of the entries above that pivot, so I'll move to my previous pivot. I want to clear this. Well, I can do that by negative 1/2 times row 2 plus row 1. That'll be negative 1/2 times 0 plus 1, which is 1. Negative 1/2 times 1 plus 1/2, which is 0. Negative 1/2 times 0 plus 0, which is 0. Negative 1/2 times negative 6, which is positive 3, plus negative 2 gives me a result of 1. Here I'm done with the Gauss-Jordan elimination, and I'm in the reduced or echelon form. From this, I can read off that A is 1, B is negative 6, and c is 8. This gives us our final answer, and we get that the function is x squared minus 6x plus 8. In Wolfram Alpha, I graphed that quadratic function, and you can see that it's passing through the 3 required points. Thank you for watching. I hope this helps you understand Gauss-Jordan elimination just a little bit better. Hope you have a great day.